Hey guys, today we're going to be solving a very basic forces problem involving block on a ramp. So, two blocks have different mass on a pulley ramp system. Determine the acceleration of the system. So, when you encounter a forces problem, first things first, you want to go ahead and make some assumptions. So, we're going to assume that this occurs on an Earth environment, so it's going to be gravity. We're going to assume that friction is not mentioned, so there therefore is no friction. So no friction, and the pulley is ideal because nothing about mass is mentioned about the pulley. There's only mass mentioned about the block. So, very basic forces problem. Let's go ahead and start this problem. To start this problem, you just want to make some force diagrams on your diagram. So, we have a normal force from the block pointing upward or onto the block from the floor. So this ramp is exerting a normal force upward, which is why the block is able to stay in place. And we have force of gravity going downward. I'm going to call this F of G, F1G, because this will equal M1G, which is convention. And we have a string pulling back on this block 1, so I'm going to call this tension. And if there's a tension here, then this tension right here has to be equal to the tension here, because we're assuming that the pulley is massless. Therefore, the tension must be equally transmitted along the string, the whole entire string. And from here, we can actually just do the work on block 2 as well. So block 2 will also have F2G, which equals M2G, which is just a formula. And it will also have a normal force. So we have some diagrams drawn. Oh yeah, I forgot to mention that you have to be given angles for this problem. So I'm going to call that alpha, we're going to call this theta. You need to be given angles or else you really can't solve this problem. So I'll also give you some angles on the ramp. And if you do a bunch of trig, you're going to end up finding that the angle here will equal the angle here. And same thing goes for this part. Angle here will equal the angle here. So this is alpha. Now, let's go ahead and transfer these free body diagrams into workable diagrams that we can draw equations from. So I'm going to say that this is the x-axis. I'm going to say that this is the y-axis, specifically for picture 1, where I deal with block 1. And same thing over here, y-axis here, x-axis here, specifically for picture 2. So these are two separate pictures. I'm going to get equations from these two pictures. I'm going to use those equations, put them together, and I'll show you how. So for block 1, I'm going to invert it just like how I drew it here. So this is my y-axis. This is my x-axis. And we have a normal force. Can't forget about that. We have tension pulling back. Okay, that line is completely slanted. And we have a line pulling this way. And that would be our F1G. And don't forget the angle theta is right here. And yeah, we can actually now make equations with this diagram right here. So let's go ahead and do that. Let's go ahead, since we're solving for acceleration of the system, it doesn't tell us how heavy each block is and doesn't tell us the angle, so we're going to have to assume a direction. I'm going to assume it goes this way. As long as you stay consistent in your assumption and you work this way to be positive, then your answer should come out correct. And the sign of the answer should tell you if you're wrong or right. If the sign is negative, then your acceleration goes that way. That's acceleration negative. Okay, so I'm going to work the problem assuming acceleration goes this way. And you're allowed to do this. Let's go ahead and solve the problem now. And to start this, we're going to look at our free body diagram and we're going to ask ourselves, what is the force in the x direction? You can also start with the y direction, but later on I'm going to show you why y direction is useless in this specific problem. So sum of forces in the x direction equals m1a, because I'm dealing with just block 1. I'm not putting block 2. I'm omitting block 2, cover block 2 for now. This is just block 1. And these have the same acceleration because the string has a tension all throughout. So as long as the string is not torn, then they'll have the same acceleration. So if we look at over here, what are some sum of forces equals m1a. So we have a force pulling this way, which is the same as this one right here. So if we were to draw some vector diagrams, you can see there's a little triangle here, and the angle opposite is sine. So we're looking at this specific component right here, which is the same as this. So all I did was I translated this down here to that. I just moved the vector. It doesn't change the problem. So that vector would be m1g, which is f1g. That's the same thing, m1g. This is just notation, by the way. This g should not be this big. It should just be notation. f1g, yeah. f1g equals m1g, and opposite of the angle, sine theta. That'll be pulling rightward, so this has to be positive, and we see a tension pulling leftward, so that has to be negative tension. And that equals m1a. That equals the acceleration of the block. Now, I could do sum of forces in a y direction. Real quick, I'll show you why this is useless. Sum of y, this block is not going up or going down in the y direction in my y-axis, so it's just going to be 0. That's a big 0. And it's just simply going to be normal force going upward. We're going to call upward positive minus m1g cosine theta equals 0. Oh yeah, this has to be n1, by the way. This is specifically for n1, because this is the normal force for block 1. See how this doesn't help us right here, because n1, cool, I saw for n1. What does that do for us over here? That does nothing. So that's pretty much useless. But if you have a problem that involves friction, then you would have to care about that. Now let's go ahead and do block 2. Block 2 has a normal force right here. I inverted my picture once again. Inverting helps in a lot of cases when you do forces. Please don't keep it like this. Don't make your x-axis for the whole diagram like that, y like that. It will be a nightmare. Just make individual diagrams, invert your graphs for each individual ones, like how I'm doing it. It makes the problem way easier. Now, and we have a tension going this way. Okay, cool. So once again, sum of forces in the x direction for this specific diagram. I forgot to say 2, but this is for block 2, m2a. Once again, this a is the same as this a because they're attached. So let's go ahead and see. Rightward positive, this tension positive. So T minus, if we draw out this one right here, this is actually just two vectors added together. We're talking about this vector, and we can just move that up here like what we did for the first one if we want to, but we can also keep it down here. I keep it down here so I can just see from the trig what it is. So T minus, it's going to be F2G, and that's just M2G. M2G sine of alpha equals M2A. Now, we just need to solve for acceleration. So, we have two equations, two unknowns. Tension's unknown, acceleration's unknown. Tension unknown, acceleration unknown. Therefore, we can put these equations together. And there's many different ways to do that. You can do substitution, elimination. I'm going to go ahead and do substitution because it's a lot simpler to understand. So I'm going to go ahead and solve for t over here with this first equation. All I'm going to do is just subtract this over here and add t to the other side. So I'm going to end up getting t equals m1g sine theta minus m1a. We can go ahead, plug this all the way over here. I'm going to write this whole thing, m1g sine theta minus m1a minus this part right here, sine alpha, that equals m2a. And the question asks for acceleration, so let's go ahead and isolate the accelerations. We're going to do that by adding this to this side and factoring it out. So add both sides by m1a. This is going to be m1a. This goes away. And if we can factor the a out, and I'll rewrite it right here. Sine theta minus m2g sine alpha equals m1 plus m2 times a. And then from here, really simple, divide both sides by m1 plus m2, m1 plus m2, and this will be our answer for acceleration. And if the question asks for tension of the string, simply just plug this over here and you'll get your tension as well. So thank you for watching and hope you succeed in your courses.